and we are going to continue with the talk that shifts to the mobile world. And the brand new startup, perf.dev, and one of its founders, Leland, is going to tell us about implementing the most precise method tracing in the industry.
Hey everyone, thanks all for attending this talk. Really excited to be speaking here at Performance Summit 4 on behalf of perf.dev. What we'll be diving into today is how we've implemented the most precise method tracing in the industry. And that's a bold claim, but we'll get into the technical details of how we've actually achieved that. But first, just a little bit about who I am. My name is Leland Takamine. I'm the co-founder and CEO at perf.dev. And before starting perf.dev, I was working at Uber for about 5 years. I was the mobile platform tech lead there and worked on a lot of cool stuff. A lot of what I worked on was in the architecture side of things. So I built out our dependency injection system, migrated our company over to that system. And aside from architecture, one of the big areas that I worked on was mobile performance. So that's obviously how I got into this space. And for Uber, this was annually hundreds of millions of dollars worth of impact, this problem of mobile performance. And the initiative was kicked off back somewhere in 2017. And a lot of what we did was we talked to some of our peer companies to understand what the landscape looked like. What are companies doing at that time in terms of solving this problem of mobile performance? And what we found, surprisingly, was that many of these companies didn't really have a strategy, and we're talking about leading mobile companies here. So it's surprising to find that there weren't many best practices in terms of how a company should address their mobile performance problem. So what that meant for us was that we needed to really pave the way ourselves in terms of how we solved this. So we spent a lot of time and resources really diving in and developing a strategy for solving mobile performance. And luckily, I was a part of being able to work on this problem at scale. And we developed a lot of strategies and tooling and built out a lot of technology that really helped us solve this for Uber. So what I realized, fast forward to today, was that not much has changed in the industry in terms of how people are looking at mobile performance. And yet this problem has been around for a while. And what I realized was that there really needs to be a company focused on just this problem because the industry deserves a real solution here. So our mission at perf.dev is to give mobile teams complete confidence in their mobile performance strategy. And this idea of confidence is really important to us because what we've found is the tooling and the strategies available today do not give teams and companies confidence in their mobile performance strategy. So we'll talk a little bit about what is that strategy. So, we learned a lot in working through this at Uber, but what does that strategy look like, in general? Well, the first thing is that a company needs to root cause their performance problems. So just understanding why the app is slow, right? That's the first step. And this is exactly what we did at Uber as well, as we took a step back and thought about, okay, well, how do we actually get visibility into what we were looking at the time was app startup. So how do we get visibility into what's happening during app startup to figure out why it's slow? Well, there is some tooling available, Android Studio profiling, for instance. But what we found out pretty immediately is that the tooling available today is not precise enough to actually debug the problems that we were seeing, because when a company has a performance problem, typically that's not caused by a single issue or a single source. What happens is it's an aggregation of many small micro inefficiencies that all add up to this big performance problem. So what you need is really precise tooling. And what we were finding is that the tooling available to us introduced too much overhead and distorted the performance profile of the application that it was measuring. So of course, when you distort the performance profile of what you're measuring, you can't really trust the data that's coming out of that tool, and that's what we were finding. So what we ended up doing is, well, firstly realizing that would be a fundamental limitation and blocker for us for debugging this problem. So what I did was I built a tool at Uber and open sourced it. It's called Nanoscope. And what this is it's a tool that gives you much higher fidelity and much higher precision in terms of visibility into the performance runtime of your application. And that's actually what we've been building on top of at perf.dev, is that open source Nanoscope project to build our debugging emulator. And I'm about to give you a demo here, but very quickly here, the benefit of the debugging emulator that we have at perf.dev is that it provides extremely low overheads, so you can really trust the data coming out of that tool. So let's hop over to our console here. And what you're looking at now is the perf.dev console. The UI is pretty bare bones. We're early on here, and we want to leave flexibility for really working with our early partners and ensure that we can make sure that we're tackling and adapting to all the use cases that come up at this early stage. But getting into the debugging emulator here, the first step when you want to diagnose a performance problem is you need to load up that version of the app. So let's say we're looking at diagnosing an interaction in the Google I/O app. So we'll install Google I/O here. And you can see that pretty quickly that app's installed. And what we're looking at now is our debugging emulator streamed to the browser. And you can see that Google I/O is installed here. We'll go ahead and open up that app. And let's say we're looking at the performance of clicking on this Get Started button. So the first thing we do is click Start Tracing, and then click on that Get Started button, and then stop tracing. We'll go and save this trace. It's a little while to save because we're tracing every single Java method invocation that occurred during that interaction. And this is where you'll do most of your investigation. We can dive in here and we can see that a lot of the time is spent in view inflation, as it often is. So one strategy would be to look at this and say, okay, is there a way that we can go back to our code and optimize this layout to reduce this time spent in view inflation? So that's kind of the typical workflow, and then you would, after making the code change, you would trace that interaction again and ensure that this time has decreased. If you're familiar with, Android Studio profiling, for instance, this will be a very familiar workflow to you. Benefit again being that you can trust this data a lot more because it introduces very little distortion in the timings, so you can see. You'll be able to trust that these durations are actually correct. Now, of course, you can come back and trace another interaction if you want to, or retrace that interaction again. But let's take a look at some of the other features here that exist today. One thing that's nice is all the traces are saved, so you have a full history of all of the traces that you've recorded in the past. You can also share these traces using a link. And then also, all of the APKs that you've uploaded are saved to your account, so you can quickly go back to profiling a previous version. So that's kind of the base functionality of our debugging emulator, and it's still really early on, so there's a lot of future functionality planned, like building more intelligence on top of that trace data to automatically surface issues, for instance, highlighting interactions like clicks and swipes, things like that. But that is the base functionality and the base workflow that you would be looking at in terms of how you would use perf.dev to debug and root cause performance issues. Now, we talked a lot about, we mentioned a few times the low overhead instrumentation of this debugging emulator. So what I want to do is take a quick interlude here and dive into how that actually works, right? We're claiming the most precise method tracing in the industry. So how are we actually getting to that point? Why is it so efficient, right? So what we've done is we've, again, based our debugging emulator on top of the Nanoscope open source project. And this is kind of how it works, right? Well, first you need a place to record and store your trace data that you're recording during the trace. So what we've done is we've put this, allocated an array of data inside of this thread data structure inside of the Android open source, in the Android open source project in the ART runtime. And what we do on every method entry and method exit is record just the bare amount of data that's required to reconstruct this trace after we've stopped recording, right? So we have this on method entry method and the on method exit method, and each of these are called every time a Java method is invoked. So where do we need to call those methods from? Again, we want this to be called on every Java method invocation. And the first place we need to modify is the interpreter. So every interpreted Java method flows through this do invoke method. So it's a very convenient spot to put our on method entry and on method exit calls, right? Now, unfortunately, not all Java methods are interpreted. So that makes the implementation a bit more complex. But you know, the only other place we need to instrument is the compiler, because some of these Java methods are JIT compiled to translate them into machine instructions to be executed directly. So what we need to do is, in the same way that we instrumented the interpreter, we need to have the compiler generate the same instructions to log those bits of data that we need to reconstruct the trace, right? So I won't get into the details of what this code actually is, but basically what we're doing is generating the same instrumentation for the compiler that we're executing in the interpreter. Now, this is kind of the fundamentals of how our tracing is implemented. There's a lot of code that we've written to actually tie everything together, make sure everything works and we can get the data out of the emulator. But this is kind of the base functionality and the base implementation. And it's not a whole lot, right? And that's kind of the point, is that the instrumentation should do as little work and the bare minimum of work to be able to pull the data out of the emulator and reconstruct the trace after you're done recording. So cool. You know, for those of you whose eyes have glazed over at this point, feel free to tune back in. We'll come back to now the rest of what constitutes a successful mobile performance strategy. So we've talked about the debugging emulator in order to that we use to root cause performance problems and how that's implemented. But what do you need beyond debugging tools? Because what we know is that just reacting to performance outages, for instance, and regressions, and having a SWAT team of developers go in and diagnose and root cause a problem, even if they have really great tools to do that, you want a more systemic solution here that allows you to catch these problems before they happen, right? You don't want to always, you need a proactive strategy to prevent these from happening, from occurring over time, right? So when we talk to companies and ask them about what their performance strategy looks like, a lot of them are gravitating towards APMs because this is a kind of a traditional solution that was used for server-side development and web development. And for web and server-side development, it's actually a pretty effective strategy because you can simply roll back your previous deployment and your users will get that fix in a matter of minutes, right, when you detect these problems in production. Now for mobile, if you detect a problem in production, it's already too late. And that's because there's this long release cycle, right? You have to wait multiple weeks for your end users to get any sort of fix that you release to production. So our recommendation here is don't use users as guinea pigs. You really want to catch these problems before you release to production, because any signal that you get from end users already is indicating that you're going to be losing users due to this poor performance problem. So what is the alternative? The alternative is automated testing here. The benefit, again, being that you can catch these problems before releasing to end users, and then your teams can move fast without worrying about shipping performance problems, because we know that in CI we can catch these problems before they get released. So that's exactly what perf.dev is providing, is an automated performance testing platform. And let's talk a little bit about how we're implementing this. Now, when companies and folks that we've talked to are thinking about automated performance testing, a lot of times what comes up are physical device labs, right? Now, what we've learned about physical device labs is that it's really expensive. So just the devices themselves, maintenance of those devices, all the hardware infrastructure that's required to set that up, it's really expensive. We've spoken to folks who are spending tens of millions of dollars just maintaining their device lab. And also what we're seeing is that they're not stable. Even at that level of investment, it's really difficult to maintain a stable physical device lab. Now, beyond that, physical devices are exactly the wrong infrastructure to be building on top of for performance testing. And that's because physical devices are inherently inconsistent. We've all had our phone heat up after using an application before and haven't have their phone slow down. So we know that there's a problem with thermal throttling. And if you imagine, we're taking off-the-shelf consumer devices, throwing them into a server rack, and then running thousands of automated tests on them. They're not built for that, and you're going to have failures and you're going to have inconsistency. And then finally, the last challenge with the physical device lab is that you have limited parallelism. So you're restricted to the number of devices that you have physically inside of your lab in terms of parallelism. So what that means is that you have a hard cap on how quickly you can actually execute the number of tests that you need to get accurate performance results, right? So what are we doing at perf.dev to address these problems? Well, we're basing our performance infrastructure on emulators in the cloud. So what this gives us is very high precision results, because we're building on top of cloud providers whose entire business is based around guaranteed consistency and stability, right? So we know that we're going to get consistent results out of our emulators. And we also get essentially infinite parallelism, of course, bound by cost of infrastructure, but the architecture itself and the fact that we're built in a cloud environment allows for horizontal scaling in a native fashion. So that means that we can execute a high number of tests, get a very high level of confidence in a short amount of time. So those are kind of the two main pieces that we're tackling at perf.dev initially, is our debugging emulator for root-causing performance problems, and then automated testing in order to catch these problems from happening in the first place, and catching the problems pre-production before you release to users. Now, zooming out for a second here, let's take a look at the state of the world. In terms of perf.dev, we have some future work planned here. One really impactful feature that we see is a visual trace comparison. So if you're trying to determine what's changed in terms of performance between one version, version A and version B, what we're building out here is an ability to visually identify those changes in code. So you can imagine that same trace view that we were looking at with the debugging emulator, and just highlighting in that trace what has changed between the two different versions. Another piece of future work for us is iOS support. So we are a cross-platform company. We'll be building out iOS support in the near future. And then finally, device profiles. Again, we're built on emulator, so we'll be able to configure we have a lot of different levers to configure to emulate different sorts of device profiles easily. Now, taking a look at the state of the world for the industry at large, mobile performance is still an unsolved problem. Companies are still working through this and working through how to think about mobile performance. And our aim is to work with companies, leading mobile companies, to lead the charge in defining best practices and then building the tools that support these strategies, right? So right now, what we're looking for are additional early partners to help test and shape our platform. We're already working with a lot of the leading mobile companies in the industry, and we're looking for a few more to really help become, thought leaders in this space and help us form our platform and strategy here. So if you're interested, and if you think your company would benefit from some of the strategies and tools that we've mentioned here, please reach out to us. Our website is perf.dev. You can also email us at hello@perf.dev, and our Twitter handle is perf_dev. So please reach out. We'd love to talk. Thank you.
Thank you so much, Leland. It's an exciting time where mobile devices are becoming pretty much indispensable parts of our lives. So it's great to see that we now have more infrastructure and tools to help us build more performant mobile applications. And we already have a question. And in fact, that's an excellent question, because that's exactly the question that I had in mind for you. So the question is, how do you know that emulators behave somewhat similarly to real hardware devices? E.g., an emulator might have better CPU and worse I/O, I made that up, than what you'd see on a real device.
Yeah, thanks, Taras. That's a great question, and something that obviously comes up pretty immediately when we talk about performance profiling on emulators as opposed to physical devices. The way we look at it here is, well, one, we need to run experiments to actually prove this out. But based on kind of the preliminary results we're seeing, it's not actually all that different. It's about equivalent to what you would see between different hardware devices. We know that the Android ecosystem is very fragmented, and the range of different, for instance, speed of disk I/O on the devices that exist in the market right now varies largely. And relying on a single device model would be just as inaccurate as relying on, say, an emulator. So that's kind of how we look at things right now. Beyond that, what we're looking into is ways to throttle I/O, disk I/O, and network speed at the VM level in order to configure and have different levers to kind of configure different device profiles and emulate what you would see for different classes of devices. So does that kind of answer that question? What we'll be doing in the future is also publishing a white paper on this after we have kind of more conclusive results here. But yeah, that's how we're generally looking at things right now.
We actually also have in our device labs that we use for profiling, we also have proxy servers where we intercept traffic, record it, and replay it so that we reduce the variance of the network and stuff like that. But another question which is related to this one would be, what about the architectural differences? Because obviously on a real device, you're usually running on ARM CPUs, and for emulators, it's usually an Intel-based CPU, so it can be very different. And in fact, especially when you're using native libraries, your code is probably going to be extremely different, even for the same library. So does this come up as an issue?
So what we see is that generally the timings end up being generally similar on whether it be a physical device versus an emulator. Again, kind of modulo the different device model classes. But we are looking into supporting ARM emulators as well, running our infrastructure on ARM cloud servers. So that would kind of remove at least that one difference. But generally, we still see that in terms of the regressions we're catching, they are pointing in the correct direction, which is the most important thing. And you have a high level of confidence in those regressions, which means that if you follow what our regression testing is telling you, you will generally be improving your performance. And that's kind of the end goal here, right? It's not to exactly replicate exactly what some specific user scenario is. It's that you need a systemic system that will push you in the right direction over the long run, right? And that's what we're guaranteeing.
Yeah, it's just at least we've internally observed that oftentimes performance characteristics of a particular method could be extremely different based on the CPUs, just because the instruction implementation could be very different. And so that's why for cases where we still want to use emulators, just because they are obviously much cheaper to operate and much more scalable because you can have them many as you want, pretty much. We are trying to use more the consumption metrics, which is basically the stuff that doesn't rely on CPU. It's like, the memory kind of things, I/O things. So do you have some infrastructure to, I guess, focus more on the I/O side of things, which is more stable, I guess, across different platforms?
Yeah, that's a good point. Right now, it's what we're looking at mostly is wall clock duration, but I think that what you're saying makes a ton of sense to look into as well, which is measuring things that you can count that are more deterministic and more, I guess, independent of CPU architecture. Yeah.
Mm-hmm. We also have a question from Shavik Roy. He's asking, how would you compare the method tracing accuracy as compared to Perfetto or Android systrace?
Sure. I'll try to answer this as accurately as possible, but somebody in Slack, if they know more than I do, please correct me. But I believe that those tools are based on sampling. And what we have is method tracing. So this is actually intercepting every single Java method invocation. So what this gives us is much higher fidelity than what those tools could provide. And if you use systrace, you'll find that it actually doesn't show application code. It only traces system methods, things like that, and not even all of them. So what you get with our tooling, our method tracing, is every single Java invocation, whether that be your application code that you've written or framework code. So I'd say that those are kind of the main differences between the two.
Yeah, this is really cool. I'm actually, so since you mentioned that you're using instrumentation, and obviously there are certain trade-offs involved in tracing versus instrumentation. So I wonder if you have also thought about, providing some sort of higher level insights about opportunities to improve performance, which would be something, I don't know if you're familiar with Amazon Code Guru, where they actually give you, it's the new product that they have where they rely on profiling, continuous profiling, and then they comment on your PRs, for example, on GitHub PRs, where they can tell you that, this is likely to increase your performance. It's usually regress your performance because you're going to be invoking this expensive method. Or they can also give you suggestions about how to improve it. Like if you switch to a different data structure, you can potentially improve your performance. Or if you avoid locking here, you can improve your contention or whatever. Do you have something like that in mind?
And is that based on static analysis or profiling?
I think it's both. They use they claim that they are using machine learning and profile data. So they combine the profile data and use machine learning to derive insights.
Yeah, so the first step for us is definitely taking that kind of raw trace output and then surfacing common issues there. That using some, maybe obvious heuristics, right? And that's kind of the first step. Second step beyond that, figure out how to have a little bit more intelligence on top of that does something smarter than just looking for methods that exceed a certain frame duration, right? And point out if you're dropping frames or not. But all of these things are kind of definitely future areas that we want to do in terms of taking our raw trace data and then building the intelligence on top of that. What's nice for us is we know that we have essentially the most accurate data that you can retrieve from an Android device or an Android emulator because of our low overhead instrumentation, which means that we have the data integrity to be really confident in any intelligence that we build on.
Yeah, this is really awesome. I mean, it's I guess a solid foundation for all the analytics that can be built on top of it, and I hope that you'll be able to create a very rich ecosystem and also integrate it with many other tools that are available on the market in terms of visualization.
Oh yeah.
make sure that it's super easy to use and very valuable tool for everyone. Well, looks like we don't. Yeah, well, thank you so much again for taking time to present at the Performance Summit 4. It's been a pleasure, and I wish you the very best of luck with defining what mobile performance infrastructure should look like for all of us. And I hope we'll all be able to leverage it to improve our customer experience, make it delightful and efficient and smooth. Thank you so much, and good luck.
Yeah, thank you, and appreciate the opportunity to speak here. Thanks, Taras.